Hi, welcome back to Intermolecular Forces. It sounds like Star Wars. I should have Star Wars music playing in the background. Sorry, I'll try and get a soundtrack next time we do this. Intermolecular forces. Okay, these are the weak forces in between the bonds. So even though there's no negative and positive per se, there is these intermolecular forces. We'll talk a little bit more about those in Chapter 8. So something to look forward to. Don't drop the class. You won't get to Chapter 8. We won't be able to talk about intermolecular forces. Super cool things like, yeah, just trust me. Super fun. Okay, so that's happening in Chapter 8. Just know that there are intermolecular forces. And if the molecular forces are very, very weak, we have something we like to call a gas. So when you have a gas, you can predict that the intermolecular forces are very weak. So they're not holding together the hydrogen bonds. Hydrogen bonds are intermolecular forces. I gave that secret away before Chapter 8. The hydrogen bonds are not holding together very well, so you get a gas. Somewhat stronger intermolecular forces. You get, take a guess, a liquid. Not a liquid, a liquid. A liquid. So these are a little bit stronger. They're held together a little bit stronger. The gases, they're just all over the place. Once the gas goes, it like explodes all over the room. A liquid, it's not a solid, but it's kind of keeping together a little bit. The strongest intermolecular forces are solids. So just for you, not for my own, not for me, but for you, I'm going to drink some water. You can see in here, maybe, can you see that? There are ice cubes. There's a solid and a liquid. And if I leave this thing open on my desk for a couple of days, it'll a gas, right? They'll sort of bounce off, and then it'll be a gas. It'll be in the atmosphere. So this water it's just for you. It's not because I'm thirsty. And it's 102 degrees outside. It's just for this lecture. Okay, so weak molecular forces, gas. Somewhat stronger, liquid. Much stronger intermolecular forces, solid. Now, don't be confused with ionic compounds. Okay, molecular. Again, melting points and boiling points. Melting points, boiling points, still lower than ionic compounds. So even the solid of a covalent is still lower than an ionic compound. So don't let that confuse you. Okay, molecular solids have lower, just write it down, lower melting and boiling points than ionic compounds. So they still have, just like I said earlier, lower melting and boiling points. They are, what do you think they're going to be? Soluble or not soluble? Come on, take a guess. Not. They're not soluble. Not soluble in water. And, come on, do or do they not conduct electricity? Come on. Think about it. Of course they don't. And I guess I have to put to be grammatically correct. They do not conduct electricity. So they are useful if you do not want electricity conducted through you. So what is a molecular formula? A formula that shows the numbers and kinds of atoms in one molecule. Now, remember, molecules different from ionic compounds. In one molecule of a compound. Molecular formula. So that is just a formula that tells you, 2H2O, molecular formula. Okay, but if I want to know more, I can go on. I can do a structural formula. These are fun. This I can't actually write out because that's down here. This, friends, is a structural formula. This takes it a step further and tells you whether you have double bonds or triple bonds or single bonds. A representation that shows connections among atoms using lines to represent covalent bonds. Wow, with the spelling right there. Covalent and among. Okay. So that is a structural formula, kind of like this. You can take that a step further. You can make a Lewis structure. These are fun. These show both connections and locations of lone pair electrons. Lone pair valence electrons. Sorry, let's add to that. Valence electrons. So you're going to use a Lewis structure if you have a bunch of lone pair valence electrons. So if you realize that you have a negative or positive charge, something's going on and something's weird, and you're like, hey, I've got this hydrogen that, you know, it's like a -1 or a +2, and I want to show that some way, and the Lewis structure alone, I mean, a structural formula alone doesn't do that, then you're going to need to use a Lewis structure and make a little dot there to say, hey, this guy has an extra electron or doesn't have enough electrons. So that's really common. You use just the structural formula if nothing weird is going on. If something weird is going on, then you need to add Lewis structure by drawing the little dot. And what is our lone pair? Just to remind you what the lone pair is, it's a pair of electrons. A pair of electrons that is not used for bonding. So if you have a lone pair, you're going to have to use the Lewis structure in addition to the line structure. We will draw some of these in class. It will be super fun. Polar covalent bonds and electronegativity. Okay, so this is the part where I tell you that I've been lying to you for the first part of this chapter. Because I do that. I just lie. I tell you things and then it's a huge lie. So if two atoms are joined by a covalent bond, they differ greatly in electronegativity. They're actually not as nonpolar as you might think. There's some small electronegativity happening. So basically it's back to the bully thing again. So in some cases, the bully's just going to take the teddy bear, right? Give it to me. You know, you got a candy bar, I'm taking it. Maybe we can hang out after that, but nonetheless, it's now my candy. I've taken it. It's not yours anymore. With covalent bonds, we're sharing, right? I'm sharing. But this is like the, where's my water? Here's my water. So in this case, oxygen is a little bit of a bully. So oxygen is bigger. I don't know if you can actually tell that, but oxygen is bigger. Trust me, oxygen is bigger. If you look on the periodic table, you will see that it has 8 shells, so it's going to be bigger. It's bigger, it's fatter, it's got a higher molecular weight. It's going to take more things from the hydrogen. So the pull on the hydrogen is going to be great. So hydrogen is like little, and oxygen is like, come on, try it. I'm sharing, I'm sharing, I'm sharing. If you have brothers and sisters, you are completely aware of this concept of sharing. Technically, I'm sharing because I'm letting them touch it. But in reality, sharing is not actually happening. That's what's going on with this water molecule. The oxygen is a bully. It hasn't taken it, so it's not as big of a bully as an ionic compound, but it is pulling more than its share. So what kind of charge does it have? What happens when we take things from people? You have a negative emotion. It has a slightly negative, slightly. It's not an ionic compound. It has a slightly negative charge. It's covalently bonded, but it has a slightly negative charge. Okay. Polar bonds and okay, what is polar bonds? Why do I feel like this? Okay, polar covalent bond. What is it, people? I'll tell you. It is a bond in which the electrons are attracted more strongly by one atom than another. The ability of an atom to attract electron is called electronegativity. There's a chart. Yes, but you can also use the one I gave you, and you will see that electron negativity increases this way, and it increases this way. So fluorine is the most electronegative. You can write that. You are probably going to want to add that to your periodic table of elements. Okay, so electronegativity, super important, super fun, super interesting. And I didn't blank these out, so you kind of get in free things. Fluorine is the most electronegativity, is assigned a value of 4. All things are less than that. Everything's less than fluorine. You want to be fluorine. If you're not, you're not 4. Metallic elements have low electronegativities down here. Halogens and reactive nonmetals have higher electronegativities up here. Again, it generally decreases going down the periodic table within a group. Now, how do we know if things are polar covalent, nonpolar covalent, or just ionic? We use subtraction. Yes, folks, it's the math. Oh my gosh, so much math. Okay, so what are we going to do here? Let's look at some just for fun. Okay, so we have, let's say carbon. Why is that underlining things? I don't know. Okay, let's say we have carbon and bromine. Okay, carbon is what? Carbon is 2.5, I'm looking, and bromine is 2.8, giving us a difference of 0.3. Look here, what does it say? This is a non-polar covalent bond. Easy. This is not rocket science, people. I promise you, this is not that hard. Okay, so let's pick some more from our super fun chart right here. Okay, more from the super fun chart. Let's pick silicone and iodine. Those are fun. 1.8 minus 2.5. Forget that these will like actually be negative numbers. Just ignore that part. And you get 0.7. What is this guy? This is a polar covalent bond. This will have a slightly negative charge, so you need to treat it as a polar covalent bond. Okay, let's do one more. Okay, what about lithium and chlorine? Okay, and we have here, I don't know if we're gonna have enough room for this. 1 minus 3. What does that equal? That equals, basically, it equals 2. What does that mean? That means it's not a covalent bond, people. That means, hello, it's an ionic bond. It's a charged bond. It's ionic. We're going to treat it like an ionic bond. It's not sharing anything. One has taken from the other one. It's not sharing. It is ionic. So we use subtraction. You check with your little electronegativity chart. I will give you this on a test. You have it for your homework because it's right here. It's also in your book. It's not a secret. So you're just going to subtract. Just subtraction. What else do I want to tell you? Polar molecule extras. Some bonds may be polar, making the molecule polar itself. Yay. Symmetrical molecules may be nonpolar, even though they contain some polar covalent bonds. Those things are just weird, and I'm telling you so you know, so that you don't come back to me and say, why do you lie to me all the time? You're such a liar. You constantly lie to me. I know there's some weirdness. I know not everything obeys that rule. I'm letting you know that that's possible. I'm not going to ask you these kinds of things on an exam. This is free information just for you. Now, something to look forward to. We're going to name binary molecule compounds on Monday. I know, you're so excited. We're not going to do it till Monday. I know you're so excited. I will see you Monday and we will name some things. All right, bye.